Welcome to your personal deep dive. Today, we're plunging into some really interesting source material.
Yeah, we've got a workshop video, a briefing document.
All focused on the essentials, really, of building software for computational design.
Mm-hmm. And it's less about just, using the tools you already have,
Right.
and more about understanding the foundational ideas for creating those tools.
Exactly. Think of this deep dive as maybe a shortcut, a way to understand how computational designers actually take complex ideas, data, algorithms.
And turn them into functional digital software, real tools.
Yeah, we're here to pull out the most important nuggets of knowledge from these sources.
Everything from the specific coding environments.
All the way up to the sort of mindset involved.
Precisely, the higher level thinking in structuring a design tool.
Okay, let's unpack this then. So right off the bat, the sources make it pretty clear that building this kind of software isn't, one size fits all.
Not at all. There are different places you can build it.
You mean like native versus cross-platform?
Exactly. The sources draw that distinction. You can build something specifically for one operating system.
Like, say, a native app just for Windows, using C# or C++, maybe.
Right, leaning on their UI frameworks, WinForms, WPF, that sort of thing.
Right.
Or, on macOS, iOS, you're in Apple's world, their frameworks.
Right.
And this is often how tools like, say, Rhino or Grasshopper handle extensions, right? They have these deep ecosystems.
So you're kind of tied into that specific environment.
You really are.
But the sources also pointed out a big advantage with something like Unity.
Oh, yeah. They really highlight Unity. It's presented as a really powerful option.
Why is that?
Mainly because it simplifies cross-platform development so much. The takeaway is basically you can develop your software, your algorithm, visualization, whatever it is, once in Unity.
Just once.
And then potentially deploy it across Windows, Android, iOS, other platforms pretty much simultaneously.
Wow. Okay, so if you need, wide reach for some geometric computation tool.
That's incredibly efficient.
Yeah. Developing once, deploying everywhere. That is a huge efficiency gain.
Definitely.
And speaking of efficiency and structure, the sources talk quite a bit about the design process itself being a pipeline.
That's a really core concept they push. Computational thinking, handling events. They describe it all as fundamentally structured, like pipelines.
Just organizing the flow. Data, operations, step by step.
Yeah, exactly. Sequential steps.
So which seems to tie directly into component-centric programming. That was another key idea.
Yes, absolutely. Crucial in many modern environments. Think about how Unity works with its game objects.
Okay.
A game object is basically just an empty container, right? An entity.
And you add things to it.
You attach components, like a transform component for position, rotation, scale.
Or like a material for how it looks.
Precisely. You build up complex behavior, complex visuals by plugging in these modular components.
So it's almost like assembling with digital Lego bricks.
Yeah.
Building functionality piece by piece.
That's a good way to think about it, yeah. It shares principles with object-oriented programming, sure, but the emphasis is really on composing entities by adding or removing these distinct bits of functionality.
And that modularity helps manage complexity.
Oh, absolutely. It's key as your software gets bigger.
That makes sense.
Yeah.
Keeping things manageable. Okay, let's shift gears a bit. The visual side. Actually getting 2D and 3D graphics onto the screen.
Especially on the web, right?
Yeah, let's start there. Web graphics.
Okay, so the sources give a good overview. For 2D vector stuff, you've got SVG, scalable vector graphics.
Based on XML. They're like DOM objects in the browser?
That's right. The big benefit there is scalability. Because they're vectors, defined mathematically.
You can resize them without losing clarity. No pixelation.
Exactly. Great for icons, diagrams, things that need to look sharp at any zoom level.
And the other main 2D way is the HTML canvas.
That's the pixel-based approach. You get a drawing context, and you use these, pretty low-level APIs to draw shapes by basically telling pixels what color to be. The sources point out that even complex shapes on a canvas at that low level are really just built from points and lines.
So it's either math shapes with SVG or drawing pixels with canvas.
Pretty much, for 2D web graphics.
Okay, vector versus pixel. Makes sense. What about 3D on the web? That sounds like more heavy lifting.
It certainly is, yeah. The sources really zero in on libraries like Three.js and Babylon.js
As the main tools.
as the kind of go-to tools for Web 3D. Yeah. These libraries sit on top of even lower-level browser APIs like WebGL or the newer WebGPU.
Oh, okay.
The sources call Three.js and Babylon.js raster engines at this sort of higher application level.
So they handle the really complicated graphic stuff for you.
They abstract it away, exactly.
Yeah.
You probably wouldn't want to touch raw WebGL or WebGPU calls unless you were like a serious graphics programmer.
Right.
These libraries give you a much friendlier way to build and manage 3D scenes.
And even for a basic 3D scene, the sources say there are essential components you always need, no matter the library.
Think about it, yeah. Every 3D scene needs, well, a scene, an environment to exist in.
Okay.
You need a camera to define what the user sees from what angle.
Makes sense.
Lighting, absolutely critical. Without lights.
It's just blackness.
Right. And then you need the actual things you want to show, which are usually represented as meshes.
A mesh. It's like the points, the vertices, and how they connect to make faces.
Exactly. And the sources emphasize that a mesh in these libraries has two key parts.
Okay.
It's geometry, that's the mathematical shape, the vertex positions, the face connections, all that.
Structure.
And it's material, which defines how it looks. Its color, texture, how shiny it is, if it's transparent.
How it reacts to those lights we mentioned.
Precisely. You need both the form, the geometry, and the surface properties, the material, to actually see something rendered.
Geometry plus material equals a visible mesh.
Yeah.
Got it. That's a
Yeah.
clear breakdown.
Mm-hmm.
Now, moving from just seeing things to interacting with them, how does the software respond when you click or move the mouse?
Event handling. Yeah, the sources highlight a couple of different ways to structure this, different architectural patterns.
Okay.
One common way is object-specific event handling.
Where each clickable thing listens for itself. Like every button, every bit of geometry has its own listener waiting for a click.
Exactly, which can work fine, but if you have lots and lots of objects,
Hundreds.
thousands.
Yeah, it could get computationally expensive, or it's just really hard to manage all those individual listeners.
Okay, so what's the alternative they talk about?
Top-down event handling. They describe this as more centralized.
How does that work?
Instead of every object listening, the system itself tracks the input, like where's the mouse, what button is down.
Right.
And then the system figures out which object is under the cursor at that moment, maybe using spatial data structures like grids or trees to do it efficiently.
And then it tells that object.
It tells that specific object, hey, you were just clicked, react.
Huh. It sounds more like having one manager directing traffic. It kind of is. The sources note this top-down approach is actually very common in CAD systems.
Why is that?
Well, it allows for more central control over the whole interaction pipeline. It can make it easier to implement complex selection logic or manipulators, things like that.
I see. So it's a trade-off, really.
Yeah.
Distributed listeners versus centralized control.
Exactly. A fundamental architectural choice.
That's a really interesting distinction. And regardless of which approach you take, the sources really push for separating concerns, right?
Oh, definitely. That's critical advice they give. Keep your core design algorithms separate from the UI code, the interaction code.
And keep both of those separate from the rendering engine.
Yes, absolutely. It just makes your code base so much more organized, easier to debug, easier to update, easier to reuse parts later.
It sounds like just good software practice, generally.
It is, but especially important in complex systems like design tools. It's a fundamental principle for building anything robust.
That separation sounds vital. Okay, so beyond general CAD principles, the sources also touched on software development for mapping and GIS specifically.
Right. They mentioned local map APIs, but really pointed to the professional-grade WebGIS APIs.
Like ArcGIS API, Mapbox.
Exactly. Those are the kind of tools you'd use for building sophisticated mapping applications online. You use their APIs to layer your own spatial data onto their base maps.
And there's a fundamental concept there you absolutely have to deal with. Projection.
Oh, absolutely critical. Taking latitude and longitude from the, curved Earth.
And flattening it onto a 2D screen, or even a 3D virtual globe.
Requires careful projection. These APIs handle a lot of the complex math involved, thankfully.
But you still need to understand the concept.
You do. The APIs give you tools to control the map view, the zoom, the styling, and make sure your data shows up in the right place on the map.
So the APIs provide the map infrastructure and projection handling, and you bring your own data layer.
Pretty much, yeah.
Okay. Now, building entirely new software is one thing. But the sources also discussed adding features to existing tools.
Right. Plugins and add-ons, super common. Software like Rhino, Grasshopper, Threads Max, tons of others.
They provide SDKs, APIs.
Exactly. Software development kits or application programming interfaces that let you write your own code to extend what the tool can do.
Making custom commands or new panels or components.
All of that. And the sources actually gave a little glimpse into Grasshopper component development.
Oh, yeah.
Showed how you define the inputs, define the outputs, and then write the core logic in a specific function. They call it solve instance.
So that's the heart of the component. What goes in, what comes out, what calculation happens.
That's it. It's a very structured way to add new nodes to that visual programming environment.
And tying into extending tools, there's a really strong recommendation in the sources about building your own personal toolkit.
Yes. This was presented as almost like non-negotiable for efficiency.
What was the advice?
Basically, as you write functions or classes in Python, C#, whatever you're using, if you find yourself reusing a piece of code,
Don't just copy-paste it.
no.
Yeah.
Package it up, put it into your own personal library or package. Don't reinvent the wheel every single time.
Build your own foundation of reusable code blocks.
Exactly. It saves so much time and ensures consistency across your projects. It's just a smart habit to get into.
That makes a ton of sense. Build your own arsenal.
Mm.
Okay, and finally, the sources briefly mentioned real-time graphics engines like Unity and Unreal.
Mm-hmm. Powerful raster engines, as they called them earlier, primarily designed for highly dynamic, real-time stuff.
Games, simulations.
Interactive architectural walkthroughs, that kind of thing. Unity got highlighted again, mostly for its ease of use, relatively speaking.
And Unreal.
Noted as being very powerful, maybe specializing a bit more in, like, super high-fidelity rendering.
But steeper learning curve.
Generally, yeah, that's the perception.
Okay.
They both serve a similar purpose, rendering 3D content fast, in real time, but they offer different workflows, different strengths.
Got it. Wow. Okay. We've covered a huge amount of ground there.
We really have.
Different places to build software, web, local, cross-platform, how visuals work, 2D, 3D, how interactions are structured,
Pipelines, components.
specific domains like GIS, the value of building your own libraries, plugins.
And those real-time engines like Unity and Unreal.
It's really the foundational technical building blocks, isn't it?
Indeed. It's been a look at the kind of the technical scaffolding you need to think about when you're going from computational design ideas to actually building the tools to make them happen.
Okay, so what does this all mean then? We've taken this deep dive into the technical essentials.
The nuts and bolts.
Yeah, but the source material, interestingly, doesn't just stop there. It leaves us with something else, a powerful, kind of provocative thought about meta-cognition.
Yes, meta-cognition. The source material defines it pretty simply. Thinking about one's own thoughts, whether they are right or wrong.
So not just learning stuff or getting skills.
No, it's about critically evaluating how you think, the assumptions you carry around, the paths you just automatically follow without questioning.
It's about questioning the conventional path, right?
Yeah.
Not just doing something because, well, that's how it's always done or that's what everyone else is doing.
Exactly.
And the source uses a fantastic, really simple example to illustrate this. The Fosbury flop in high jump.
Oh, yeah, that's a great one. For decades, high jumpers use techniques like the straddle or the scissors kick.
Going over the bar facing forwards or sideways.
Right. It just seemed like the obvious way, the right way to clear the bar.
Until Dick Fosbury came along.
And he used this completely different technique, jumping essentially backward over the bar. And at first, people thought it was ridiculous.
It was widely ridiculed. Looked absurd, apparently.
But he had thought about the problem differently, right? He questioned the right way, the assumed way.
To jump, and his seemingly counterintuitive approach.
It completely revolutionized the sport. It's basically the standard technique now.
Because someone dared to think about their own thinking and challenge the norm.
Which raises a really important question, I think. How can you, the listener, apply this idea of metacognition to your own design process, to your research, to the projects you're tackling, especially now in this fast-changing world of data, AI, computation?
What assumptions might you be holding on to about the right way to design something, or the right tools you must use, or the right methods that might actually be worth reevaluating?
Are you just following the crowd, maybe? Or are you really stepping back and evaluating if there could be a better path? Even an unconventional one.
Like Fosbury finding a completely new way to get over the bar.
It's about having that courage, maybe, to think about your own thinking And potentially challenge the status quo.
A really, really thought-provoking idea to wrap things up.
Definitely.
And as the source material suggests, building software for computational design, understanding all this, it's an ongoing journey.
Always more to learn.
So keep learning, keep exploring the examples and references from the material we discussed, and keep fine-tuning your understanding.
And maybe, just maybe, keep practicing that metacognition.
Throughout your design career.